Jnanam Paramam Dheyam. Knowledge is supreme.
So now what we do is, now that we have done a little bit of sketchy discussion of how spectra are recorded, now we go on to discuss actual spectroscopy of certain kinds. And remember, the questions that we are asking to start with is, how do you determine molecular parameters? In quantum mechanics, you have studied things like bond length, bond strength, right, bond angle. Now, okay, those who have been in my class, for them again this is a cliche, but Max Planck had said that everything, the experimental results are the only truth. Everything else is poetry and imagination. Not to undermine poetry and imagination, but we should be able to see things experimentally. How do I determine experimentally how strong a bond is? How do I determine experimentally how long a bond is? By spectroscopy. And the first kind of spectroscopy we are going to discuss tells us how long a bond is, bond length. And that spectroscopy is rotational or microwave spectroscopy, right. Of course, at least once in the class I should show you the entire electromagnetic spectrum so that I have a clear conscience. I can never remember all this, so you also do not need to remember, but you kind of know what it is. We are focusing in this part of the electromagnetic spectrum. The most important relation, as we have said 3-4 times already in this class, is your Bohr resonance condition, h nu equal to E2 minus E1. Different parts of electromagnetic radiation come in resonance with different kinds of energy gaps. This is the first one that we see, we write in terms of energy, frequency of time scale. UV vis, these are the values, right. Just look at the frequencies, 10 to the power 15, 10 to the power 12, this is what we discussed in our, when we talked about your Fourier transformation, and microwave is 10 to the power 9 hertz, okay. These are the kind of frequencies. Now, UV visible essentially is, when you do UV visible spectroscopy, you explore those electronic levels about which you have studied in detail in your quantum chemistry class at stage 4 to 5. IR and microwave discuss nuclear motion. IR talks about vibration, microwave talks about rotation, okay. And the reason why we can neglect one kind of spectroscopy while dealing with another kind is provided to us by this Born-Oppenheimer approximation. I believe Born-Oppenheimer approximation is known to you. What does it say? What is Born-Oppenheimer approximation? Yeah? Can we rise above a murmur? Okay, Manthan, tell us. So, what Manthan is saying is that when we consider movement of electron, we can neglect the movement of nucleus because they take place in different time scales, right. So, in other words, what Born-Oppenheimer approximation says is that this problem is completely separable. You can separate different parts of the component. So, Hamiltonian is sum of different Hamiltonians, wave function is product of different wave functions. So, when that happens, you can, as you know, separate the problem into different components and you can worry about one problem at a time. Of course, Born-Oppenheimer approximation does not always hold. Breakdown of Born-Oppenheimer approximation is not all that uncommon, and when that happens, things get a little more complicated. But to start with, at least, we are going to work within the ambit of Born-Oppenheimer approximation. So, what we do is we pretend, when we talk about rotational spectroscopy, we pretend that the molecule is rotating and not doing anything else. We do not worry about anything else. Let us go right away to the rigid rotor model. We are talking about a rotating molecule. To keep things simple, a rotating diatomic molecule, okay. And to do this, we first of all need to build a model that fits this situation. And the simplest model when you have a diatomic rotor is a rigid rotor model, right. Once again, we have studied this in physics course 11 and 12, rigid rotor, two bodies connected by a rod rotating with respect to each other, okay. Two body problems are always, well, it sounds very funny if I say two body problems are problematic, but so let us say two body problems are not easy to solve, right, complex. What do we always do whenever we have a two body problem? we try to reduce it into a one body problem. And in case of rotation, it is not very difficult to reduce it also. How do you reduce a two body problem to a one body problem? By the use of center of mass, right, and what is called reduced mass, right. Yeah. So, let us say this is our molecule HCl, we want to study it, two body problem. It is not very difficult to reduce it into the problem of a single body with reduced mass mu rotating about a massless center with radius of the circle being radius of gyration. Any question? Okay. Okay, radius of gyration, say R0. Now, of course, spectroscopy, as we said, is quantum mechanics in action. So, first thing that you have to do is set up Schrodinger equation, and what you need for Schrodinger equation is you need a wave function and you need a Hamiltonian. Now, you people have studied hydrogen atom problem, right. Hydrogen atom problem is a central field problem. So, it was expressed in terms of your spherical polar coordinates r theta phi, and in this r was a coordinate of one kind, it was a length, and theta phi together, since both are angles essentially, they make up another kind of coordinates, that is angular coordinate, right. So, now see, when we talk about something that is a rigid rotor, it is rotating with unchanged R0. Would we agree if I say that the Hamiltonian is going to be identical to that of the angular part of the hydrogen atom problem? Same Hamiltonian that we have in hydrogen atom, except for the fact that if you remember the hydrogen atom Hamiltonian, what is the r part of the Hamiltonian? It has a del r, then del 2 del r2, things like that, right. Now, if r does not change, what will be the first derivative or second derivative with respect to r, right. So, r is not changing at all, so we do not talk about it. So, what we are left with is that del theta del phi kind of terms. So, the Hamiltonian that we have essentially boils down to the angular part of the Hamiltonian that we had for your hydrogen atom problem. Okay. What will the wave function be? What is hydrogen atom wave function? In the simplest possible term that you can think of. Now, when I say simplest possible term, do not tell me psi. Huh? It is a product of an r dependent part, theta dependent part, phi dependent part. Is that right? Remember, for hydrogen atom, what did we say? Psi equal to r dependent part multiplied by capital theta, which is dependent on small theta, and capital phi, which depends only on small phi. Now, when I try to talk about a rigid rotor, I do not need this one, right? Right? Because r is fixed. The only parameters that I have are theta and phi. Yeah. So, the wave function that I essentially have is capital theta multiplied by capital phi. Okay? And as you know, this is called spherical harmonics. Right. So, we already know what the Hamiltonian is, we already know what the wave function is. Now, let us think what the equation would be. Does anybody remember what the angular part of hydrogen atom wave function stand for? Hydrogen atom Hamiltonian stand for? Is it related to some physical quantity? Angular part of the Hamiltonian? Which physical quantity would it be related to? Angular momentum, exactly, it is related to angular momentum. So, if I ask a little further, how can it be related? So, it is an operator, right? How can it be related to the angular momentum operator? And how can we get energy from there? Okay, let us see if you remember this. Do you remember that this L square operator operating on y, which is function of theta phi, what does that give you? What is the value of square of total angular momentum? L into L plus 1 multiplied by h cross. We all remember this? Here what we will do is just to remind ourselves that we are not talking about hydrogen atom, but we are talking about rigid rotor. We are going to write not L but J, capital J. So, this would give you J into J plus 1 multiplied by h cross square. Do we all agree with this? If there is a question, please ask. No question? What is J? J is the rotational quantum number. Which quantum number of hydrogen atom is it analogous to? L. What are the possible values of J? J 0, 1, 2, so on and so forth. Okay. Now, let us see if we can write the expression for energy. Now, if you remember your rotational dynamics, what is the relationship between rotational energy and angular momentum? L square by 2I, isn't it? L square by 2I. What is I? Moment of inertia. And what is that? Mu r0 square. Very good. Do you understand what I am writing? Energy, rotational energy is given by square of angular momentum divided by 2I, where I is your angular momentum, which is, no, what am I saying? Moment of inertia. Moment of inertia, which is equal to mu r0 square. Okay. So, on the left hand side, so this is my equation anyway. On the left hand side, if I divide by 2I, I should divide the right hand side by 2I as well. So, I will divide right away by say 2 mu r0 square. Okay. Let us expand a little bit. J into J plus 1 multiplied by h square divided by, what is h cross? H cross is h by 2 pi, right. So, h cross square is h square divided by 4 pi square, 4 multiplied by 2, that is 8, 8 pi square mu r0 square. There is something that I did not write and nobody corrected me. Yes. So, this is my equation. From here what I can write is energy for rotational level J is given by h square divided by 8 pi square mu r0 square multiplied by J into J plus 1, and this is energy in say joule. Okay. So far so good, right? Whoever has studied rotational spectroscopy, I think knows this by heart anyway. Okay. Now, generally in rotational spectroscopy, we prefer to work not with energy in joule, but wave number, centimeter inverse. How do I go from energy to wave number? E equal to h nu, yeah, equal to h c nu bar. So, nu bar should be E by h c. So, you do not have to remember anything really, you can just work things out if you forget. So, if I want epsilon j in centimeter inverse, then I just have to divide by hc, and what you get is h divided by 8 pi square mu r0 square j into j plus 1. Oh, I did not write C, I said it. Okay. Now, if you look at this, h is a constant, 8 of course is a number, pi is a constant, c is a constant, mu is a constant for a particular atom, it is not a universal constant. Same is true for R0 square, right. So, for a particular molecule, I can call this a constant B, but we have to remember that this constant B is a characteristic of the molecule we are studying. It is not a universal constant, please remember that. Okay. So, this is your expression epsilon j equal to, do not forget epsilon j is in centimeter inverse, Bj into j plus 1. Okay. Since the rest of the discussion is easy, I will just quickly go through them in the slides. Okay, this we have discussed already. This is your 8 pi square IC. Now, selection rule, as you know, is delta j equal to plus minus 1. Next day, we will start with the discussion of why it is delta j equal to plus minus 1. Even that will come from the wave function. Okay. For that, you should do some homework in case you have forgotten. You should go back and read your hydrogen atom notes once again. Hydrogen atom is very important, it keeps coming back to haunt you again and again. You need to remind yourself what is actually the form of the theta dependent part of the wave function. Can you tell me? This theta dependent part into r dependent part of wave function, right? That's what am I saying? Theta dependent part into phi dependent part. So, phi dependent part I remember, it is e to the power im phi. What is the theta dependent part of the wave function? Which polynomial? Laguerre, Hermite, Legendre, none of the above. Legendre polynomial, right? These polynomials were named after a mathematician who was a legend. So, his name was Legendre. No, not really. His name was Legendre, he became a legend. Nothing to do with each other, right? Let him alone. Don't. So, Legendre, right? These are Legendre polynomials. Do you know, Legendre polynomial in what? For this wave function, is it Legendre polynomial in x or y or z? Or none of the above? None of the above. So, what is it in Legendre polynomial in? Not theta, cos theta. Do not forget, it is Legendre polynomial in cos theta. Okay. And do you know of the recursion formula? How these Legendre polynomials are related to each other? Okay. That is what we will need, we will discuss it next day. Fine. For now, let us just live with the fact for 3-4 days that selection rule delta j equal to plus minus 1 is there. If that is the case, delta E would be 2b into j plus 1. I am not done. I still need 5 minutes more. Delta E equal to 2b into j plus 1, right? So, you are familiar with this energy ladder, I hope. This is very simple. You just plug in the values of j into this expression. You will see these are the values that you get, and the take home message from here is that energy gap keeps increasing as you go higher up the ladder for a rigid rotor. And the spectrum actually goes through a maximum. Even before we talk about why it goes through a maximum, first thing we should understand is the energy gap, the gap between lines is equal in all cases, because you see this is one transition, right? This transition is what? 2b. What is the next transition? 0 to 6b is 1, but then you can also have 2b to 6b. So, 2b to 6b, that is the next line, that is 4b. Next line would be 6b to 12b actually. So, these lines are going to occur at 0, 2b, 4b, 6b, so on and so forth. The gap between two successive lines will always be your 2b. And that brings us to the application of microwave spectroscopy in understanding bond length right away, because you know that B is h by 8 pi square c mu r0 square, right. So, everything else is known. If you can experimentally determine B, well, I am assuming that you know that it is HCl. So, you know what is atomic weight of hydrogen, atomic weight of chlorine. Then the only unknown in that case is R0. So, right away from this spectrum you can determine the bond length of a diatomic molecule using a rigid rotor approximation. Okay. So, next day we will start from the question, why does the spectrum go through a maximum? Okay. Now you can leave.